The next group that we have in the periodic table is the nitrogen family. Nitrogen family is the group. As you can see, now we are in the right side of the periodic table. We started in the left and now we are in the right side. Okay? So this nitrogen group, also known as group 15, it begins with nitrogen, sorry. Okay? And all of them are going to have very similar characteristics. We're going to have two nonmetals that are going to be nitrogen and phosphorus. Okay? Two metalloids that are going to be arsenic and antimony. And one metal that is bismuth. I really like bismuth a lot. It's one of my favorite elements. Because of what I showed you the other day, the bismuth crystals, they are very beautiful. You can see it here in the picture, by the way. But even in that picture, you're not able to see the beauty of bismuth crystal, sorry. So, well, those are the elements that are making up this group. Nitrogen is most commonly found as atmospheric, and 2 is a diatomic gas, by the way. Phosphorus as phosphate rock, and arsenic, antimony, and bismuth can be sulfides or oxides. That means that they can be found in nature in a way in compounds or combined. But antimony and bismuth, the last two elements, they have the characteristic that they can be found in nature as free elements, pure elements. That means elements that are not combined. So antimony and bismuth, you can find them both combined in a compound or as free pure elements. Okay. Then they range from very abundant elements like nitrogen and phosphorus, okay, to relatively rare elements like arsenic, antimony, and bismuth. Bismuth is very beautiful metal, but at the same time is a rare element. I mean, that's why it's gonna be expensive. Nitrogen is very abundant. It doesn't mean that is cheap, but that is gonna be a lot cheaper than bismuth, for example, because of the amount that it can be found in the Earth's crust or in the atmosphere. All of them, they consist in atoms that contain 5 electrons in the outermost level. So if you see nitrogen ends in 2s2, 2p3. That means that they have 5 electrons in the outermost layer. Phosphorus, 3s2, 3p3. Okay? 2 plus 3, 5 electrons in the outermost layer. This one, arsenic, in the outermost level is 4. Okay? So in this level, you will find 2 electrons from 4s2 and 3 electrons from 4p3. Okay, so we have 3 electrons in the outermost level here. Same gonna happen in antimony, 2 and 3 makes 5, and same for bismuth. 6s2 and 6p3 are making the 5 electrons in the outermost level. So, common characteristic in all of them that they share 5 electrons in the outermost level. What type of bond do they form? They form covalent bonds, okay, or covalent compounds. And the most common oxidation number are going to be +3 or +5. So if you see in your periodic table, you're going to notice those oxidation numbers. For example, in nitrogen, it says ±3, 5, 4, 2. Okay, even though you can find all those oxidation numbers, the most common ones are going to be 3 and 5. They exist in 2 or more allotropic forms except nitrogen and bismuth. They are solid at room temperature except nitrogen, which is a gas. Okay. Phosphorus is a, an element that we can find easily in our house. Why? Because the matches, they contain phosphorus. That's why they have that reddish color. Okay. The match head is made of phosphorus, and also the strip on the matchbox. Okay, where you are where you rub the match. Well, that part is also contains phosphorus, and the friction between the two, the match head and the strip, is that's what creates heat, which in the end that's fire. Fire is another state of matter. Now, another allotropic form of phosphorus is this white phosphorus. This one, as you can see, it has to be kept underwater because it catches on fire when it is exposed to air. So this phosphorus, the white phosphorus, is going to be unstable because it's going to be very reactive. It's going to react with air, so it's going to set on fire. It needs to be kept underwater. And the black phosphorus and red phosphorus, the red phosphorus is the one that you can find in the match. They they are stable, okay? They can be exposed to air and nothing wrong is going to happen. Then we have the oxygen family. Of course, the oxygen family is going to include oxygen, okay? And is the family or the group number 16. It contains the elements oxygen, sulfur, selenium, tellurium, polonium. What are the characteristics? They can occur naturally as free elements or in combined states. One of the most common elements that are found in nature is sulfur. I don't know if you have visited a thermal bath. I don't know if you have visited thermal bath or aguas termales. I don't know if you have visited. They have a certain smell, like an egg. That smell, the smell you feel, the smell that you feel over there, it's because of the sulfur, and that occurs naturally in underground deposits. Okay, in places where volcanoes are. Why? Because of the high temperature. Okay, because of the gases that are coming out of the volcano. So even though, I mean, thermal waters, okay, aguas termales, they're nothing more than evidence that volcanoes exist in Honduras. The only difference is that they are not active. Because there are volcanoes, we have sulfur. Sulfur is one of the most abundant elements that we have. And the smell, as I told you, it's like an egg, like a boiled egg. It's weird. It's very, I don't like it. Well, anyway, it's very common. Um, it consists of three nonmetals that are oxygen, sulfur, and selenium. Okay? One metalloid that is tellurium, and a metal, a post-transition metal that is called polonium. Consists of atoms that have 6 electrons in their outermost energy level. Same idea, okay? If you do the electron configuration of oxygen and you add the electrons in the outermost level, you will find 6 electrons. You can do the same for sulfur, 3 plus 4, 6 electrons. You can do the same for selenium, 2 and 4, 6 electrons. Tellurium, 2 and 4, 6 electrons, and polonium, 2 and 4, 6 electrons. So you can see all of them are going to share the 6 electron in the outermost energy level. If you don't trust me, I invite you to do all the electron configuration, and you will notice it. Now, these elements, they tend to form covalent compounds. Covalent are molecular compounds, okay? So they will form covalent bonds. They exist in several allotropic forms, and they tend to exist as diatomic and polyatomic molecules. Because they are non-metals, they can exist as polyatomic molecules. One common one is, well, two common ones. Oxygen. Oxygen gas exists as a diatomic gas, okay? And it exists as just O2. That is oxygen. And O3, for example, yes, it is oxygen, but 3 atoms of oxygen is what we know as the ozone, like the ozone layer that we have in the atmosphere, okay? So yes, you can do the same with hexasulfur, okay? You can see they're polyatomic. Polyatomic means that they have multiple atoms, okay? More than just one atom is going to be a polyatomic molecule. And this is a very important thing. They commonly exist in compounds with an oxidation charge of -2, but they often exhibit other oxidation states. So the most common oxidation state is -2. The most common oxidation state is -2, but that doesn't mean that the rest are going to be using just -2. So in this picture you can see how sulfur looks like. In the color it is yellowish. That's why the egg yolks have this color too. When you boil them, they look exactly yellow. This exactly yellow. That is because of the sulfur content that they have. Now another structure that sulfur has is this orthorhombic shape. Orthorhombic. Orthorhombic because the shape is like a rhombus, okay? And as you can see, it has luster. It is like a crystal. So this is the crystal structure that sulfur element has. Now this one right here is again sulfur, but it's showing a monoclinic shape. As you can see, it looks like a tiny box. Okay, it has like a rectangular shape. And again, sulfur exists. Okay, well, as I told you, sulfur is one of the most abundant elements as well, and it can exist in nature combined. It can be pure, okay, like the sulfur that you can find naturally in those deposits, or it can be combined with other elements to form minerals, as you can see right here. Now this is my favorite family. I think that if I was an element, I would be in halogen. Probably nobody thinks that. I regret about saying it. I'm sorry, it was a joke. Halogen family. The halogen family is that group of elements that is right before the noble gases. The noble gases is the last group. Okay, and this halogen family contains these elements: fluorine, chlorine, bromine, iodine, and acetylene. These are very common elements, and we're going to be working with them a lot in the chemical reaction. I mean, in the practice problems, halogen family is one of the most common ones, and it's going to be used very often. All of them are non-metals. All of them are non-metals, okay? And they can occur in nature combined or in metal halides. Metal halides is when you combine a metal with an element from the halogen family. So it contains these elements, and you will see that they consist of atoms that have 7 electrons in the outermost energy level. Fluorine, 2s2, 2p5, 2 and 5 make 7. Chlorine, 3s2, 3p5, 2 and 5 make 7, and so on. Okay, so you can see that all these elements share the same amount of electrons in the outermost energy level. They are found in rocks of the Earth's crust, but they can be dissolved in water, in seawater, sorry. They range from fluorine, that is one of the most abundant elements, to acetylene, which is one of the rarest. Okay, so the abundance of this element, well, is going to vary a lot. That's why they have a huge range. They exist at room temperature. Room temperature is the temperature that you have right now next to you, okay? Surrounding you. That's the room temperature. So at room temperature, they exist as a gas, like fluorine and chlorine, or liquid, like bromine, or like a solid, like iodine and acetylene. So in what physical state are you going to find this halogen family? In the 3 physical states. They can be gases like fluorine and chlorine, or they can be liquid like bromine. Bromine, I think, is the only liquid non-metal that we can find. I'm not very sure. I think it's the only one. The only one that is liquid. Yes, it's the only one that is liquid. Bromine. In the periodic table, you can see that some elements look red. Red represents that they are a gas. Blue represents that these elements are liquid. And as you can see, bromine is the only liquid element that is part of the known metals. And those that are black are solid. So acetylene and iodine are solid. Now this is important because this is the topic that we're going to be seeing next week. These elements tend to gain 1 electron to form a halide, X minus ion, but also they share electrons and they have positive oxidation states. Halogens are nonmetals that they can form ionic compounds or that they can share electrons to form molecules. They are reactive. These are the most reactive nonmetals in the whole periodic table. And fluorine, my friends, fluorine, this guy, oh my god, this guy is the greatest one. Fluorine is the most reactive element from all those known metals. Now take a look here in this picture. Halogens are the only family that contains elements that represent all the 3 states of matter at room temperature. That means that they can be solid, liquid, or gas. Chlorine is here in the first flask. As you can see, the color that it has is a gas, okay? But the color that it has is yellowish. Between yellow, green, in my opinion, it looks more yellow than green, okay? But scientists know better. When they discovered it, they thought that it was green, so it should be a little bit green, okay? Now, this one right here is bromine. Bromine is a liquid non-metal, and it has this color like brown, okay, reddish brown, orange, like that. This is the color for bromine, and it is liquid. And iodine, like I showed you the other day, as you can see, these are solid particles, and it is black, bluish, purple, okay. So you can see that elements from this group, they show the three physical states. And here is like the video that I showed you the other day, the sublimation of iodine. Iodine is sublimes to produce a pilot vapor that it recrystallizes in the bottom of the evaporating dish that is filled with ice. So this one is filled with ice to lower the temperature. Once the temperature is low enough, this vapor, of course, is going to rise because that's what vapors do. They rise, okay? And once this vapor touches this dish that contains the ice, it becomes a crystal. So it is a really nice experiment that you can do with iodine. Sadly, we don't have a chemistry lab, okay? But the good news is that at least we have the technology to find videos and see these reactions. In my school, in my school, we had a chemistry lab, and I never saw iodine, for example. So having a chemistry lab is not going to be a guarantee that you're going to be seeing all the possible chemical reactions because of many reasons. Elements could be abundant or not. The rarer they are, they're gonna be more expensive. So having a chemistry lab is not going to be a guarantee that you will see all these chemical reactions. And in the last group, we have the noble gases. Oh, they are nice. I have to say, they are nice. I mean, okay, wait. Um, no se ve bien. Okay. Okay, the noble gases. The noble gases are very easy to find. They are in the last group in the periodic table. All of them, as you can see, all of them are gases. That's why they're called noble gases. So the physical state is gas. The noble gases were among the last naturally occurring elements to be discovered. So when scientists were finding the different elements, noble gases were the last one to be found. Okay, the last one to be discovered. Scientists assumed that noble gases could not form compounds only because they are unreactive. But in 1962, the inorganic chemist Neil Bartlett created compounds from xenon and fluorine. Now, this combination, xenon and fluorine, xenon is almost in the bottom from all these gases. And fluorine, as I told you, is the most reactive non-metal, okay? But despite all this, these elements from the group 8A or group 18, they're still known as noble gases because of their stability. Noble gases, they all gonna have, well, except helium, they all gonna have 8 electrons in the outermost level. Let me show you this. Okay, look, neon, 2 and 6, they have 8 electrons in the outermost level. Argon, 2 and 6 is 8. Krypton is this one. 2 and 6, 8 electrons. Xenon, the outermost level is 5. And you have 8 electrons. Radon, the same, okay? But what happens with helium? Helium is the exception of the rule because helium has only 2 atoms. Two electrons. So it is impossible for helium to have 8 electrons in the outermost level. So except for helium, the rest of the elements of the noble gases are going to have 8 electrons in the outermost energy level. Noble gases readily react because of their stable electron configuration. I mean, all the electron configurations want to be like noble gases. So all these elements, all elements want to be stable. They want to form stable compounds. To have stable compounds, they need to have 8 electrons in the electron configuration. But you can see only these elements have 8 electrons. I showed you all the electron configuration of all the elements during all these days. And except noble gases, the rest of the elements don't have 8 electrons. So what do they want? They want to act like a noble gas because they want stability. Helium is pretty much the most abundant element in the universe, okay? It is very light. That's why the helium balloons rise until you don't get to see them anymore because they are very light. They are lighter than air, imagine. And this helium element was discovered in the emission spectrum of the sun. Okay, so scientists were analyzing the spectrum of, okay, every element has a different spectrum. Okay, so scientists were analyzing how the sun looks like, and they found a spectrum that they didn't know. Afterwards, it was found that helium was the responsible of that emission spectrum of the sun. So they discovered helium in the sun, but in the end, okay, in the end, is one of the most common elements that we have. Maybe not here on Earth, but there, outside Earth, okay, surrounding planets. In planets, we're gonna have helium a lot. It's gonna be very common. Still, it's common. It's very common. Helium is the lighter than air gas, okay, that we use here in the balloons that I was telling you. A mixture of helium and oxygen is used by deep sea divers, okay. So as you can see, to make it is safe. Yes, it is safe. That's why they are noble gases. They are safe, okay. So okay, that's how safety an element is. Their ability to react. The transition metals, I don't know if you remember, but I told you the transition metals, they barely react. That's why they are safe to be touched, for example. Same happened with helium. Helium, or the rest of the noble gases, they are noble. That's what noble means, okay? In other words, it's not going to be harmful to you. So these deep sea divers, they use a mixture of helium and oxygen just to dive. And the helium is gonna make them to go to the surface easily because of how light it is. Right. sorry. Okay, and neon. One of the uses that we have for neon as an element is that it's commonly used in lights. Okay, that's why we say neon light. Okay, that's what it means. That those are lights that are that we can see because of the. This is like the characteristic of neon. Okay, the color that it have, the color that it shows, how bright it is a characteristic of the neon gas. We are going to